In biomedical research, accurate cell counting is more than just a technical task. It's a cornerstone of disease diagnosis, treatment evaluation, and scientific discovery. From tracking immune cell infiltration in cancer to monitoring neuronal density in neurodegenerative disorders, the number of cells in a microscopic image often determines the course of clinical decisions. Yet despite decades of progress, traditional manual counting remains labor-intensive, subjective, and impractical for high-throughput studies. Enter deep learning. In recent years, density map estimation, where a model predicts a continuous heat map representing cell density, has emerged as a powerful alternative. Unlike object detection or segmentation, which struggle with overlapping or densely packed cells, density estimation handles crowding gracefully. Models like CSRNet have pushed the boundaries, adapting techniques from crowd counting to count cells in complex, high-density environments. But here's the catch. While these models are accurate, they're also black boxes. They give you a number, but not why. In medicine, where decisions can mean life or death, transparency isn't optional. Clinicians need to understand how a model arrives at its count, not just that it does. That's why interpretability has become a critical frontier in AI for biomedicine. Most existing interpretability methods were built for classification. Think GradCam or class activation mapping, where you visualize which regions of an image influenced a label. But what about regression tasks like cell counting, where the output is not a class, but a spatially distributed density map? Until now, there was no method that could provide both accurate predictions and meaningful, visual explanations for density map estimation. Today, we introduce CountXplain, a novel, prototype-based framework that integrates interpretability directly into the density map estimation pipeline. This is the first method to embed a prototype layer into a density estimation network, enabling the model to learn representative visual patterns for both cells and background artifacts, without sacrificing accuracy. Here is how it works. At its core, CountXplain builds on a pre-trained CNN feature extractor, like CSRNet, frozen to preserve its learned knowledge. The extracted features are then processed through a feature map processing layer, applying a 1x1 convolution followed by a sigmoid activation. This normalizes the features and prepares them for comparison. Then comes the key innovation, the prototype layer. This layer contains two sets of learnable prototypes, cell prototypes and background prototypes. Each prototype is a vector in the same feature space as the processed feature map. The model learns to associate certain visual patterns in the image with these prototypes. For every spatial location in the feature map, the model computes the squared L2 distance to each prototype. These distances are converted into similarity scores using a log-based transformation, creating a similarity map, a heat map showing how closely each region of the image matches each prototype. Now, here's the magic. The final density map is generated by combining these similarity maps with learned weights from a 1x1 convolutional layer. Each prototype contributes to the final count based on how well it matches the input image, just like a team of experts voting on the presence of cells. But to make this work, we need to train the model properly. That's where our multi-objective loss function comes in. First, we have the density estimation loss, standard mean squared error between predicted and ground truth density maps. This ensures the model counts accurately. Then comes the prototype to feature loss, a new term designed to guide the learning process. For cell prototypes, we push them to be similar to regions in the image with high cell density. For background prototypes, we do the opposite. We encourage them to match areas with minimal cell presence. This forces the model to learn distinct, meaningful patterns for both cells and non-cell elements, like debris, staining artifacts, or out-of-focus regions. Finally, we introduce the diversity loss, a critical component that prevents prototype collapse. Without it, multiple prototypes might learn the same pattern, becoming redundant. The diversity loss penalizes excessive similarity within each group, cell, or background, using a thresholded cosine similarity matrix. Only off-diagonal elements above a certain threshold are penalized, ensuring that prototypes remain distinct and capture a wide range of visual variations. The result? A model that doesn't just count cells, it explains how it does so. Let's see it in action. On two public datasets, DCC, with average 34 cells per image, and IDCIA, with up to 141 plus or minus 120 cells per image, CountXplain achieves counting performance on par with state-of-the-art models like CSRNet and SauNet. In fact, it slightly outperforms XPRT, a self-interpretable regression model with a lower MAE, proving that interpretability doesn't have to come at the cost of accuracy. But the real win is in interpretability. We conducted a preliminary survey with 3 experienced biologists. They were shown red-boxed regions in test images, patches where the model's similarity to a prototype exceeded the 99th percentile. Then they were asked, what does this region represent? And how easy was it to tell? The results were striking. For cell prototypes, the agreement among experts was 97.25%, with 91.7% of samples achieving perfect consensus. The average ease rating was 2.69, meaning most were classified as moderately easy. Only one sample with a rare morphological pattern was harder to interpret, suggesting that the model can be refined further in edge cases. For background prototypes, the results were even stronger. Same 97.25% agreement, but with a perfect ease score of 3, all responses were rated easy. This means the model reliably identifies artifacts like staining noise, dust particles, or out-of-focus areas, giving biologists confidence that the model isn't mistaking noise for cells. And when we look at the global knowledge, what patterns the model learned from the entire training set, our visualizations show clear, distinct clusters. Cell prototypes capture different cell types, sizes, and staining intensities. Background prototypes reveal consistent patterns of non-biological interference. These aren't random blobs, they're meaningful, domain-relevant representations. We also ran ablation studies to validate our design choices. When we removed the diversity loss, prototypes collapsed. Background prototypes clustered tightly, failing to capture variation. Without the prototype-to-feature loss, the model lost direction. Background prototypes started resembling cell prototypes, blurring the line between what's biological and what is. And when we tested the sensitivity to the similarity threshold tau, how strict we are about diversity, setting tau equals 0 forced the model to be too rigid, causing it to miss subtle cell patterns. But allowing a small degree of similarity, tau, enabled the model to capture richer, more relevant features. All of this confirms that CountXplain isn't just a post-hoc explanation tool. It's built into the model from the ground up, ensuring that interpretability is not an afterthought, but a core function. In short, CountXplain delivers accuracy through density map estimation, transparency through prototype learning, and actionable insight through visual explanations that biologists can trust. It's not just a model, it's a collaborative tool. Researchers can now ask, why did the model count this many cells? And get an answer that's not just a heat map, but a visual narrative, showing which patterns the model recognized where they appeared, and how they contributed to the final count. This is a major step toward trustworthy AI in biomedicine. Where models once operated in secrecy, now they can show their work, making deep learning not just powerful, but understandable. And the future? We're exploring dynamic prototype allocation, where the number of prototypes adapts based on image complexity. We're also planning larger user studies to validate the method across diverse experimental conditions and cell types. Because in science, the most important metric isn't just accuracy, it's trust. And with CountXplain, that trust is finally within reach.